Thank you very much. Well, thank you, first of all, for the invitation to speak here. It's a pleasure. And I thought, I mean, I thought of what connections I could make to many-valued logic, and I'm afraid I couldn't think of something in my recent work which connects there. So I thought I would tell you about some recent work anyway, and let you think about whether there are connections. And I picked this paper, which is joined with Abhishek Shankaran, who I'm delighted to see seems to be in the audience here. This is and this paper appeared in CSL this year, where we looked at, I mean, it was motivated by looking at Seese's conjecture, which is a 30-year-old conjecture in the realm of finite model theory. We don't resolve it, but we kind of, I think, got a bit of a fresh perspective on it. And I wanted to tell you about the perspective. I'm not going to get into the technical results. I will just try and give you a broad brush overview of our perspective on it. Okay. Especially, I assume, as in this audience, much of this will be new. So let's see, have I got this? Right. So as Carlos said, this is about monadic second-order logic and graphs. So for the purpose of this talk, graphs are finite, simple, meaning undirected loop-free graphs. And monadic second-order logic is the formula for expressing properties of graphs, which formally we define by having a collection of element variables and a collection of set variables. And we can recursively define the formulas as you might expect. The atomic formulas are equality and the edge relation, and unary relations for where S is a set variable. We have Boolean combination, then we have quantification both over elements and over sets. Right? That's the monadic second-order logic of graphs. Monadic second-order logic is widely studied because, for one thing, it is highly expressive. But at the same time, when you restrict to many interesting classes of graphs, it is still algorithmically well-behaved. So it sort of gives a great balance between high expressive power and, in some ways, reasonable, tractable algorithmic behavior. And so, people look at a lot of logics, but in some sense, for many instances, this is a reference logic to compare against. And one way of thinking of this is it's a means of generalizing methods like automata theoretic methods and algebraic methods from formal language theory to graphs. In that, on finite words or even infinite words, monadic second-order logic is equivalent to automata models and also equivalent to certain algebraic formulations. Graphs are not as well behaved as things like words or trees, but as long as your graphs have certain kind of compositional structure, you can recover some of this nice behavior. So part of this is what is nice compositional structure on graphs. That's part of what the whole development of the study of MSO on graphs looks at. But I'm going to talk about two computational problems. In fact, I'm going to focus very much on the first one, but I thought I would mention two that people look at. What do I mean by algorithmically well-behaved? What does it mean for the logic to be algorithmically well-behaved? One is, we're going to consider two algorithmic problems. One is the satisfiability problem for a class of graphs. I give you a sentence, and is it satisfiable? Is there a graph in the class which makes this sentence true? And the other is what I call the evaluation problem. Many people call the model checking problem. If I give you both the sentence and the graph, tell me whether the sentence is true in the graph. Okay. Now, the second one, given that we're talking about a class of finite graphs, is always decidable. The question is, what is its complexity? For satisfiability, the question is usually whether it's decidable at all for a class of graphs. Now, if you consider the class of all graphs, this is not well behaved, right? This is kind of as wild as it gets. Satisfiability is undecidable. Already we know for first-order logic it's undecidable. People have mentioned Trachtenbroth's theorem several times in the course of this workshop. And the evaluation problem is intractable. And by that, you can you can fix a single sentence of MSO, which defines an NP-complete problem, like graph 3 colorability. In fact, you can go up the polynomial hierarchy to any level and find complete problems there that are expressible in MSO. So in that sense, the class of all graphs is bad. MSO is much too rich a logic for us to consider. So when I say that the evaluation problem is tractable, I will mean the following. It's a version of what's called fixed parameter tractability, but just take this as our definition of tractability. Evaluation is tractable if there's a constant C, depending only on the class, so that for any MSO sentence, the decision problem, which is the set of graphs which satisfy that sentence, is decidable in time n to the C. So any MSO sentence then defines a polynomial time problem, and in fact, the degree of the polynomial can be bounded. That's what I will mean by saying the evaluation problem is tractable. Now, one sort of classic, interesting class of graphs you get is by restricting the tree width of a graph. The tree width is a combinatorial measure on a graph, which sort of expresses how tree-like the graph is. Formally speaking, well, this is not formally, this is still a fairly informal definition by picture. A graph has tree width k if you can cover it by subgraphs of at most k plus 1 nodes in a tree-like fashion. So in this picture, we have a graph on, what is it? 4, 5, 7, and 2, 9 nodes. And I've covered it with patches of these blue shapes. So 4 patches, and the largest one has 4 nodes on it. So this is a 3D composition of the graph of width 3. I think I could probably actually get away with width 2 if I did this a bit more carefully. But so the tree width is the smallest number by which in which you can cover a graph in this way. I mean, this is, as I said, not the formal definition, but we won't need that for the purpose of this talk anyway. On classes of bounded tree width, a very famous theorem of Courcelle tells us that MSO is well behaved, in that you can construct from the 3D composition and an MSO, you can construct an automaton which evaluates the formula, and you get both that the satisfiability problem is decidable and the evaluation problem is tractable. In fact, every MSO sentence defines a class of structures which is decidable in linear time, right? So my n to the C, the constant C is 1 in this case. For contrast, I consider another class of graphs, which for many other purposes is a very well-behaved class of graphs, say the planar graphs. But for the purpose of MSO, it's bad in the sense that satisfiability is undecidable on planar graphs, and the evaluation problem is intractable. So you can write MSO sentences which, well, in particular, you can, 3 colorability on planar graphs is still NP complete. So that witnesses intractability. But from my point of view, what's interesting is that you can sort of show both of these things, the intractability of the evaluation problem, the undecidability of the satisfiability problem, by coding tiling problems on planar grids. What do I mean by this? So the classic undecidable problem is, I give you a set of tiles. Can you find a large enough finite tiling system which satisfies certain constraints on the tiles? Local constraints of which tiles can sit next to each other. And a classic NP-complete problem is, I give you a fixed finite size and a set of tiles, and can you tile a grid of this size? So a grid like this is a graph which is planar, clearly. And to express the tiling problem is really to say, is there a way of coloring it so that certain local constraints are satisfied? And this is clearly an MSO. You can express it in MSO. And so essentially the same construction shows both the undecidability of the satisfiability problem and the intractability of the evaluation problem. Now, the other key notion I want to introduce is that of an interpretation. So an interpretation is a way of defining a function, or in really a relation between pairs of graphs using MSO formulas. So the idea is that I have a pair of formulas. psi v and psi e, I call them, and given a graph and an interpretation for the free variables, and I can safely assume the free variables are all set variables, right? It doesn't hurt. Given a graph and an interpretation for the free variables, we get a new graph whose vertices are the elements satisfying this, and whose edges are the pairs satisfying this formula. Okay. To make it an undirected graph, you can take the symmetric closure of this set. That's fine, because I said we would be dealing with undirected graphs only. Okay. So this is how you define from one graph another using an MSO formula. That's an interpretation. And if we have a class of graphs, and we let G range over all elements of this, and the tuple range over all tuples of subsets, we get a collection of graphs, which is basically the interpretation of C, right? It's the image of under the function this defines. Okay. Why are we interested in interpretations? Because I'm going to look at reductions between the satisfiability problem between different graphs, and this is this notion of going from one graph to another allows us to talk about reductions. So here we go. The point is, if I give you an MSO sentence, and I want to evaluate it in the graph, which is the image under this interpretation of some graph G and under A, then I can do that by evaluating a certain sentence phi star in the original graph, where I simply get phi star by replacing in phi the edge relation by its definition and relativizing all the quantifiers to psi v, right? So this is standardly, if you have an interpretation going from structures to structures, you have a translation of formulas going backwards. So evaluating the problem in the interpreted class, evaluating sentence in the interpreted class reduces to evaluating a sentence in the original class. And this reduces the MSO satisfiability problem over the interpreted class psi p to satisfiability over C, which means that since I showed you that, these grids, these planar grids, have undecidable MSO satisfiability, then in any class of graphs in which you can interpret arbitrarily large grids, you have MSO satisfiability is undecidable. Okay. And pretty much, okay, in the other direction, so sorry, I should say, if the class C can be obtained by interpretation from some tractable class like trees, some well-behaved class, then the MSO satisfiability problem on C is decidable. Okay. Now this takes us, sorry. Okay. I said this about decidability. You can say something similar about tractability, but there's a slight caveat here. Suppose we have a class of graphs in which we can interpret arbitrarily large grids, and the size of the grids is not too small, so it grows at least polynomially in the size of the graphs in which it is interpreted. Then MSO evaluation on C is intractable. Okay, so the thing is, of course, to get intractability, your grids still have to be large enough. If they're small, then in polynomial time on the size of the tiny grid, you can still do a lot. Okay. And similarly, if you can interpret the class in a class of trees, then MSO evaluation on C is tractable. Okay. So these tractability of the evaluation problem, satisfiability of the decision problem really go hand in hand very much. And that's why, I just use the notion of a class being well-behaved. Well-behaved kind of makes both of these things, well, tractable, decidable, as the case may be. This leads me to the formulation of Seese's conjecture. So, as I said, this goes back about 30 years, and Seese famously conjectured that essentially the only way to get MSO decidability, so decidability of the satisfiability problem, is if you have an interpretation in trees. So really, trees are the only decidable case, and then by interpretation, you get others. So the bounded Treewidth case is a special example because classes of bounded Treewidth for any fixed bound can be obtained by an interpretation from trees. So that is the conjecture, and it is still open. So MSO satisfiability is decidable if and only if C is included in a class obtained by interpretation from the class of trees. One direction I've told you, we know, right? If it is obtained from a class of trees, it is decidable. So the open question is really that for any class which is not obtained by an interpretation from the class of trees, MSO satisfiability is undecidable. It's usually, the conjecture is usually stated in terms of clique width, which is, another notion of, another measure of the complexity of graphs, like Treewidth, but interesting in that it allows simple but dense graphs like cliques to have low width, hence the term. Okay, formally, the definition of clique width, you don't need to know this for the purpose of this talk, but basically the clique width of a graph is defined as the minimum number of labels so that G can be obtained by a sequence of operations where you create a vertex with label lambda, right? So essentially, if you want to construct the graph G, and you are allowed the following operations: create a new vertex with a given label lambda, take all the vertices which have label lambda and all the vertices that have label mu and put edges between them, relabel all the vertices which have label lambda to have label mu instead for any pair of labels, and take disjoint unions of two labeled graphs. And through such sequences of operations, if you can construct the graph G using, let's say, at most k distinct labels, then the clique width of the graph is k. And what we know is that a class of graphs has bounded clique width if and only if it can be interpreted in a class of trees. Which means that, Seese's conjecture is saying that any class of graphs of unbounded clique width has undecidable MSO satisfiability. That's the conjecture. Okay. I'm going to strengthen this conjecture a bit, because Seese's conjecture really says that the only way to get decidability is if we can interpret the class in the class of trees. Turns out the only way we know of proving undecidability is by showing that in the class we can interpret large grids, right? And so a stronger form of the conjecture is really that those are the only two possibilities. For any class of graphs, either it interprets arbitrarily large grids, or it is itself interpreted in the class of trees. Okay, and formulated this way, it bears a sort of family resemblance to the famous the excluded grid theorem of Robertson and Seymour, which in graph structure theory, which says that a class of graphs has bounded tree width if and only if it excludes some large grid as a minor. Okay, but in the context of Seese's conjecture, when we're talking about clique width rather than tree width, for instance, and we're talking about interpretations rather than minors, a more relevant notion of graph inclusion is that of the induced subgraph relation. So basically, what in this work with Abhishek, what we were doing is asking the question, what might a counterexample to Seese's conjecture look like? Okay, and we were just going to first of all map out a little bit of the terrain of what that means. So first of all, it suffices to consider hereditary classes. By a hereditary class, I mean a class of graphs, so that if you have a graph in the class, then every induced subgraph is also in the class, right? So if you start with a graph and delete certain vertices, and you get the resulting subgraph must also be in the class. Now, it's not that hard to see that if MSO satisfiability is decidable on a class, it's also decidable on the hereditary closure of C. So the hereditary closure of C is simply you take all the induced subgraphs of graphs that appear in C. Which this is why it suffices, if we're looking for counterexample, to think only of hereditary classes. And we call this HUCW, the hereditary classes of unbounded clique width. All right, so that's the place to look for counterexample. Now, these hereditary classes of unbounded clique width have attracted a lot of attention in the graph theory literature in recent years, right? Quite separate from logic and finite model theory, I would say. And I will just give you a little sampling of the results that motivated our work. Lawson constructed a minimal class in HUCW. And I'll show you the construction in a little bit, in a few minutes. So what do I mean by minimal? That is a class which is hereditary of unbounded clique width, but no proper hereditary subclass has unbounded clique width. So really, if you remove any graph from C and remove all of its induced subgraphs, sorry, not its induced, you remove any graph and you remove anything of which it is an induced subgraph to maintain the hereditariness of the subclass, you'll get something which has bounded clique width. This was considered a great novelty at the time. This was Collins et al. Showed that you could a sort of systematic way of constructing an infinite family of minimal classes of hereditary clique width, and more recently, Brignall and Cox have shown that you can extend the construction to get uncountably many such classes. Okay, so there's a rich space of minimal hereditary classes of unbounded clique width. Now, if a class of graphs interprets large grids, then every class that contains it also interprets large grids. So does that mean it suffices to look at just the minimal ones, right, and determine whether every minimal class interprets large grids? Will that settle Seese's conjecture? Well, not quite. Because there are classes which are hereditary of unbounded clique width, but which don't contain within them any minimal such class. In other words, you will have an infinite descending chain inside of hereditary classes of unbounded clique width. So it turns out that this infinite descending chains are related to infinite anti-chains. This is something we show with respect to the induced subgraph relation. So any hereditary class which contains no minimal hereditary class of unbounded clique width will necessarily contain an infinite anti-chain, which is, I should say, an infinite anti-chain still of unbounded clique width. That's missing from the slide. But an anti-chain with respect to the induced subgraph relation. So that means in order to prove Seese's conjecture in the strong form that which I formulated it, it suffices to show that every hereditary class of unbounded clique width that is an infinite anti-chain interprets large grids, and every minimal class interprets large grids. Really, those are, kind of the two cases to consider. I'm not sure this takes us much further forward, but as I said, this is kind of laying out the landscape around this. Then the other thing we did in the paper was we surveyed all the known constructions of minimal HUCW classes, and I told you there are uncountably many of them, but it's still possible to survey them. There's a few basic constructions, and we were able to show that for all of them, they do interpret large grids, so none of them will provide a counterexample to Seese's conjecture. In many cases, the constructions, it looks very grid-like, and this is straightforward, but others less so, and I thought I would just show you one. And this is Lawson's original example of a class of graphs of unbounded clique width, which is minimal. And this is the way it's defined, right? So this is it's a class of graphs whose vertex set, let's say, is 1 through n, an initial segment of the natural numbers. And you have edges between I and I plus 1 for each I from 1 to n minus 1, right? So in other words, you have a simple path through all n elements. And in addition, you have an edge between every pair of integers of the form 2 to the AB and 2 to the AC, where B and C are odd. Okay, So in other words, if the largest power of 2 that divides them is the same, you put an edge between them. Okay. Now, the proof that this is a minimal class of unbounded Treewidth is, in fact, somewhat involved in the original. But what we show is that you can interpret by an MSO interpretation, interpret grids, which of course immediately shows you that it has unbounded Treewidth, right? And you can show minimality as well. I'm not going to give you the construction because I'm out of time and I want to leave a few minutes. So I just thought I'd let you think about this for a moment, and hopefully, there you go. There is a picture of what such a graph might look like. This is on 19 vertices. So there's a path of length 19, right? And then we've divided up the vertices by the largest power of 2 that divides them. So first of all, you have all the odd integers, all the odd multiples of 2, all the odd multiples of 4, the odd multiples of 8, and the odd multiple of 16 that's there. So each of these things within the square, within the dashed box, will be a clique, right? There'll be an edge between every pair of them. And from this, how you interpret, I mean, put this way, it starts to look a bit more grid-like, but then it takes a bit of work to extract from this an MSO interpretation, which takes you to grids. But I'll stop here and leave you with this picture and take any questions.